Good morning, boys and girls. It's Friday. It's May 29th, and today I'm going to take you through a quick review of the theory of continental drift as we move forward to learn a little bit more about the theory of plate tectonics. So the theory of continental drift was proposed by Alfred Wegener in 1912. The theory simply states that all of the continents were once together in a supercontinent called Pangea. Pangea meaning all land or all earth. Pangea slowly split apart and the pieces drifted horizontally to their current locations. Pangea, it was proposed, was the supercontinent together about 250 to 300 million years ago. Here is a nice depiction of what Pangea might have looked like. When I look at this, it almost looks like a characteristic C, like a little Pac-Man. And you can see the current day land masses labeled Eurasia, North America, South America, Africa, India, Antarctica, and Australia. And this landmass is able to be created based upon the evidence that Alfred Wegener sought out to support his idea. And a quick review, his first piece of evidence came from looking at some of the world's first maps. And he noticed the match of coastal lines of large land masses. In particular, South America and Africa, their coastlines match pretty similarly, as well as some others, North American, east coastline of North America with the northwestern portion of Africa. Both I've highlighted before. What's really important to note here with this apparent jigsaw puzzle fit of continents was that when we look at the continental, what's called the continental shelves around the continents, we actually see a much better fit. So if we take a look at this map in the upper left-hand corner of the screen, you'll see around the continents this light blue area. That light blue area is actually showing the different continental shelves that surround the continents. So boys and girls, when we live on continental crust, the continental crust actually extends further out into the ocean and is covered by the ocean. It's just areas of seabed around a large landmass where it's really shallow compared to the open ocean. The continental shelves, this lighter blue area, is actually considered continental crust. It is not oceanic crust. So when we match up the continental edges and look at the continental shelves, they're actually more of a perfect match than just looking at the edges of the land that we live on, which is really quite interesting. So Alfred Wegener's first piece of evidence he used to support his idea that the continents were together was this idea of puzzle fit of the continents. Now, it's a good piece of evidence together with all of the other evidence that he compiled, but standing all by itself, it's not really a valid piece of evidence all alone. Alfred Wegener knew that. He was no fool. He was a scientist, of course, so compiled lots of other evidence to support this gigantic theory that the continents were together. The second bit of evidence came from fossils. So went to the fossil record to see where fossils of ancient creatures were found. One of the fossils that he focused on was the Mesosaurus fossil. Now, the Mesosaurus, as a review, was a small reptile that lived on land but swam in fresh water only. Now, fossils of this reptile were found only in South America and Africa. And you can see that it's the southern portion of South America and the northern portion of Africa, the northwest portion of Africa, where we have fossil remains of Mesosaurus fossils. Now, this is really important because Mesosaurus, again, was a small reptile, and it also only swam in fresh water. Now, what's so significant about finding these fossils in South America and Africa? Well, the distance between South America and Africa is 3,000 miles, and in between South America and Africa is the Atlantic Ocean. The ocean is salt water. So Wegener would reason and argue that Mesosaurus couldn't possibly swim in the salt water and couldn't even swim the distance between the continents. So he used this as evidence to support his idea that South America and Africa definitely had to be connected. So at this point, we had South America and Africa with that uncanny puzzle fit of coastlines, and now we have the addition of some fossil evidence. Mesosaurus is just one of many fossils that Wegener used to support his idea of continents being connected. A second fossil that I'm going to introduce to you right now isn't a animal or a reptile. It's actually a plant fossil. And this plant is called the Glossopteris. Now, Glossopteris was a fern, pretty much like a tree, though, almost like a tree fern. Glossopteris is a Greek word. Glossop actually means tongue, and teres means fern. So it was like tongue fern. And it gets its name, if you look at the fossil remains here in the lower left-hand corner of the screen, the leaves of the fern almost were tongue-shaped, so that's where it gets its name, Glossopteris. Now, Glossopteris fern fossils are found embedded in rock on 6 different land masses. They're found here in South America, in this dark green area here in Africa. This number 3 here that I'm pointing to, that's Madagascar, India, Australia, and Antarctica. Now, what's so significant about finding Glossopteris fern fossils in these 6 land masses? Well, here's the big reason why Glossopteris supports the idea that these land masses were connected. If we look at where these land masses are located today, take a look at the map in front of you, you'll see that each of the land masses is located in a different climate zone. And what's really a red flag is the fact that Glossopteris fern fossils are found embedded in rock in Antarctica. Now let's talk about ferns for a little while. Ferns are a tropical plant. They grow in warm climates, warm tropical climates. Now, when we see Glossopteris fossils found in different locations on these different land masses in all varied climates, we can use this as evidence to suggest that these land masses must have been together at one time and in the same warm tropical climate zone when Glossopteris grew and thrived on the land. And the red flag is Antarctica again. How could there be fern fossils in the rock in Antarctica when Antarctica is 99% covered by glaciers today? Because, you know, the land of Antarctica is located in the South Pole. Furthermore, the Glossopteris was a large fern, so mostly like a tree. So its seeds were very, very large. So most plants pollinate the land by wind. Wind will carry their seeds. Of course, some animals could carry seeds, and seeds could also travel oceans if they're on a boat or if they're on a bird's back. But we have these large seeds, think of like the size of acorns, that the Glossopteris fern fossil created. And these seeds could not be carried by any of those mechanisms. Far too large to be carried by wind, which is really the number one way that seeds will pollinate, okay, and be carried to different areas. So they were far too large to be carried by wind across these vast oceans to these different areas. So Wegener used this as reason to support that the continents were together and in a similar tropical area when Glossopteris lived and thrived. So there are a couple of fossils that support his idea. Now, when we look at the map in front of you, you see there are other fossils too. We have the Synagnithus, we have the Lystrosaurus, other reptiles. 3 reptiles in total that Wegener used to support his idea. I'm going to focus on the Mesosaurus, however, for our study, because the Mesosaurus is only found in that South America and Africa. And again, remember, it was that freshwater reptile, lived on land, swam in freshwater, but small, wasn't this gigantic dinosaur-like creature. It could never swim the distance between South America and Africa, nor could it ever swim in salt water. So fossils correlate across these 6 land masses, and when we put the correlations or match the fossils together, we get something that looks like the map sitting in front of you. And when you did this with the gizmo, your Pangea, using the fossil evidence, looked pretty much like what's in front of you right now, matching the light color to light color, which suggests that these land masses were all together. A third piece of evidence that Wegener used were climate clues. And climate clues came in a couple of varieties, but I'm going to just highlight the one big climate clue, and that came from glacial evidence. So there are glacial rock deposits and glacial scratching or grooving that Wegener used to support his idea that continents were together. Let me just tell you what a glacial rock deposit is, because this has not been highlighted. If we take a look at the pictures I put on the screen, take a look at the 2 pictures in the lower left-hand corner of the screen, in the middle of the screen. The lower left-hand corner of the screen, you see this like pile of rocks? Those pile of rocks are actually called glacial till. That's a glacial deposit. So let's go over what a glacier is. A glacier is this gigantic river of ice, if you will, okay, that sits on top of continents and slowly moves over or under its own weight. It'll slowly move over the land. As the glacier moves over the land, boys and girls, it leaves scars on the land, and it will grind up the land much like a bulldozer and break up all the rock that it's sitting on top of. And it will plop out deposits of the rock that it grinds up as evidence or a tag that it was here. So this deposit of rock is called glacial till. It's glacial deposit. And just this big boulder sitting here, this actually is a picture coming out of New York in Central Park. This boulder, where did that come from? Well, that's called the glacial erratic. It's also a glacial rock deposit. So picture, if you will, the continental glaciers scouring the land, moving ever so slowly, breaking the rock underneath. And what happens is rock gets stuck underneath the ice, the bottom of the glacier, and it gets carried with the glacier for a little distance, a short while, and then slowly but surely the glacier just plops them out, almost like poops those rocks right out of them, and leaves a tag or a nice little trail of glacial rock deposits. So glacial rock deposits are found in many different locations on the planet, in particular South America, Africa, Antarctica, India, Madagascar, and Australia. So similar rock deposits, these glacial rock deposits, are found on those land masses. In addition, and this is what you have been introduced to. In addition, glacial scarring or scratching or grooving is found in the rock in those land masses as well. And in the upper left-hand corner is a nice image of glacial scarring or scratching that's actually found in land masses right here. This comes out of North America, this image, but that's a nice image of, see these nice lines in the rock? That's glacial scratching, which is an indicator that glacier once covered the area. Now, when Wegener went to the glacial record, he pieced together the land masses that had current glacial rock evidence of the same age and type and glacial scarring. When he pieced it together, he could see that it created this large circular area on the land masses that must have been the size of the continental glacier at one time. This is definite evidence that these areas, these land masses, had to have been connected. And when they were connected, they must have been in a further southern locale near the South Pole and covered by a giant ice sheet at one time. So when we look at the maps in front of you right now, this is the current position of the continents that have glacial rock deposits and glacial scarring or scratching on them. South America, Africa, India, Australia, Madagascar, and current day Antarctica. When we connect those glacial deposits and those glacial scars and we correlate, we see and we come together with this map down below, and it really shows that this area had to have been closer to the South Pole, and these continents had to have been connected. Your Gizmo glacial evidence map would look very similar to what I have in front of you right now. And again, you can see how they correlate or match up the glacial deposits. And the red arrow, boys and girls, indicates where the South Pole probably was. So Africa must have been right at the current day South Pole at the time, because when we see the border of the glaciers, we see the glacier definitely moved outward to the north and to the south from Africa. The last bit of evidence that Alfred Wegener used to support his idea came from rock clues. So the first bit of evidence came from mountain ranges that actually match across oceans. The example given would be the Northern Appalachian Mountain Range. Now, the Appalachians run along the east coast of North America. If you've ever been to New Hampshire or Maine or Vermont, to the mountains here in North America, those are the Appalachians. You've been to the Appalachians. Now, the Appalachian mountains also run into Greenland and across the ocean in Western Europe. They're called the Caledonian Mountains. Now, what's really interesting here is the rock is the same age and of the same type in those mountains. Now, what's so significant of this discovery, finding this mountain range in North America, in Europe, in portions in Greenland? Well, Wegener argued that mountains are only created as a single massive mountain range when land masses collide and the edges fold up. In order for these mountains to be found in North America, Greenland, and portions of Europe, these land masses had to be connected. And they must have been connected, boys and girls. This is a very significant piece of evidence. So the fact that mountain ranges match up across oceans also supports Alfred Wegener's theory of continental drift. His evidence is starting to be really, really strong here. Now, I'm going to introduce you to one other piece of rock evidence. So mountain ranges matching up across oceans is a definite huge piece of rock evidence, but there's also just rock structures that match up across oceans, boys and girls. And what's really interesting is we have rock structures here right in Rhode Island that correlate or match up with rock structures across the Atlantic Ocean into Africa. So now remember, when we looked at the puzzle fit of the continents, we definitely saw South America and Africa appear to fit like a puzzle. But if you looked at the east coast of North America and compared it to the northwestern portion of Africa, you would see that they seem to have an apparent puzzle fit too. Well, they do have an apparent puzzle fit, and they also have those continents, North America and Africa, have rock structures that match up. And right here in Jamestown, Rhode Island, we have an area called Beavertail National Park that shows and exposes rock that correlates with Africa. So you'll see here, this is actually me. I'm starring in this slideshow right here. So here I'm sitting on a rock formation, and you can see this rock formation looks like it's made up of layers of rock, and it is. That's sedimentary rock I'm sitting on. The sedimentary rock forms in horizontal layers. And notice that this is tilted upward. The fact that that's even tilted upward suggests that there was some kind of collision in the area to push that rock and tilt it upward. And there is evidence all throughout the rock at Beavertail National Park in Jamestown that suggests a collision occurred at one time in our geologic past. And there's also evidence of age of rock and the type of rock, which correlates to Africa. So just a quick little geography lesson. Where is Jamestown, Rhode Island? Well, here's a map of Rhode Island in the upper left-hand corner of your screen. The red island, the island that's colored red, that's Jamestown. And right at the point where I'm pointing to right now and where my arrow is pointing in the slideshow, that's the tip of Jamestown. That's Beavertail. Beavertail is named because Jamestown actually looks like a beaver's tail. That's where I'm sitting right now, right on the edge of that island. And this rock is really cool, boys and girls. If you ever have a chance to get out here to Jamestown, to Beavertail National Park, and walk the rock with your family and take a look at the geology, I would highly recommend it. So here I'm sitting again on that tilted sedimentary rock, and this is a different view, sitting again on the tilted sedimentary rock, and you can see the different colors of rock in Beavertail. You also will notice that when you look at the rock here, there are folds in the rock. So you see sedimentary rock usually only forms in horizontal, straight horizontal layers. But if you follow my cursor, you can see how this rock is actually folded, almost like a wave. That's a fold. And this rock right here is a fold. There's folds in these layers of rock. Those folds are evidence that something massive happened here in the geologic past. That is rock that has been folded and twisted and contorted. And the only thing that can do that is when there's continents or land masses meet and collide together. And there's evidence right here in Jamestown. So we have this rock structures that are all folded and contorted and twisted and not looking the way they should, that match and correlate with rock structures in Africa across the Atlantic Ocean. Same age and same type of rock are found on both Rhode Island and in Africa. Here is another something really cool about Jamestown that further supports the idea of continental drift and this whole idea of separation and colliding. So this is a nice view in the upper left-hand corner of the tip of Beavertail. This smiley face is where I actually am standing in this picture right here to the lower right-hand corner. Now, you see all these red arrows in the pictures, the three pictures I have. Jamestown, Beavertail is a location in geology where we actually see evidence of two old tectonic plates. There is a fault line. A fault is a fracture or a meeting place between two different blocks of rock. And a fault is an area where rock either A, has moved before or can continue to move. In Jamestown, there is a fault that runs right from, so the ocean, the Atlantic Ocean, this large crack, you'll see it in the upper left-hand corner, right underneath the lighthouse, this big crack in the rock. Now, the crack in the rock is actually the meeting of two different blocks of rock. So let's just take a look at the picture in the lower right-hand corner of me standing on this black rock. This black rock is called phyllite. It's a metamorphic rock. You can see there's a definite division or crack between the black phyllite and over to the right, this lighter colored stone, that's actually a metasedimentary rock it's really a sedimentary rock, but it's partially metamorphosed by heat and pressure. It is a siltstone, a type of siltstone. These are two different rock structures, boys and girls, that meet at the fault line. The fact that this fault line, and the fault line runs pretty long, is here in Jamestown is definite proof of our tectonic past where lands collided. So this fault is evidence of a time when Pangea first formed. We have that right here in Jamestown, Rhode Island. So 3 different views of the fault. Here's the fault line coming right from the ocean, okay? Here's me standing on the fault line. And for reference, I'm right about here where the smiley face is. This lower left-hand picture is the fault line coming from the ocean. So Jamestown, Rhode Island has rock structures that correlate with land across the Atlantic Ocean in Africa, which also supports the idea that continents were together. So very cool. One last thing about Jamestown while I'm at it. So Jamestown, get there with your parents. It's so cool. You love it. The rocks are cool. Embedded in the rock in Jamestown was this ancient trilobite fossil, many trilobite fossils. Upper left-hand corner is a trilobite. Now, trilobites were these ancient arthropods, invertebrates, guys, similar to modern-day horseshoe crabs. Now, fossil remains of trilobites were found all embedded within this rock. You can no longer find full trilobite fossils in the rock. They have since been chiseled out by probably geologists and maybe laymen like you and me, amateur geologists thinking things are cool. But they were found all throughout our rock. Pretty neat. But what's really cool about the trilobite is this particular species was also found in the rock across the Atlantic Ocean in Europe and Africa, only in those 2 other areas. And what's cool about trilobite, and here's the reason why this also supports the idea that the continents were together, is trilobites lived in shallow coastal environments. They did not live in deep oceans. So think about where Africa, Europe, and North America are relative to each other right now. There's a giant deep ocean between us. So Wegener could use this, not that he did use this. This discovery came in only the 1970s. We discovered the trilobite fossils. But Wegener used, remember, fossils to support his idea that continents were together. We have fossil remains and fossil evidence that was discovered in the early 1970s of these ancient trilobite fossils embedded in our rock that correlate with the rock across the Atlantic Ocean. This supports that we were once connected to Africa and Europe. It is super cool, super cool. Get to Jamestown if you can this summer. So let's wrap up the rock evidence. How do these rock structures and clues support the idea that continents were together? Well, guys, rocks only form as singular massive structures or layers over millions of years. The only way that identical rock structures can be found on different continents is if those land masses were connected when the rocks were formed. So there you have it. Wegener has puzzle fit, fossil clues, glacial evidence, and rock clues to support his idea. Tons of valid evidence. That evidence is really reliable. It supports his idea that the continents were together. And here would be a nice image of your rock evidence matching up. And here is a nice picture of Pangea. So Wegener is able to match together all of that evidence and create the map of what he thinks Pangea might look like. But he had one major fault with the theory. He had all of this evidence. It was valid. It was strong. He had enough evidence. But there was one crucial piece he could not explain. He could not explain how the continents were moving or why or what caused the continents to move. He had no explanation for the force that was moving the continents all over the world, boys and girls. And that's what led to the rejection of his hypothesis or his theory in the early 1900s. Rejected. Wegener spent his life working to support his idea, and in the end, it was rejected in his lifetime because he could not explain the how or the why the continents drifted. And there you have the story of Alfred Wegener's theory. Now, I asked you guys to think about if Alfred Wegener's theory is correct, which, you know, now, boys and girls, we know that he was very, very correct, because with the advent of technology and as we started to learn more about the Earth's surface, in particular the ocean floor, his theory actually is proven today. But we're going to get more on that as next week, we progress into next week. So when we look at the video of Pangea breaking up and the pieces drifting to their current locations, if the continents are still moving today and continue to move, what might the Earth look like in the future? I asked you this question the other day, and so many of you had some great ideas. How about I take you through what it might look like? So here is the map of current day planet Earth. I have circled in red the Mediterranean Sea and where Italy is. Italy is right here, Sicily, with the Mediterranean Sea. So watch what scientists predict the surface of the planet will look like as we move millions of years into the future. So if I just go 50 million years into the future, keep your eye on Italy. When we take a look 50 million years into the future, there is Italy circled, and I don't see the Mediterranean Sea anymore. What do you notice, boys and girls? You might notice that the sea has closed up, and we have this new land feature called the Mediterranean Mountains. Africa actually meets with Europe, and when that happens, it thrusts up the mountain range and closes up the Mediterranean Sea. And if you look a little more carefully at the map, you might notice Antarctica in the south is now moving a little bit further northern, and a portion of Antarctica is exposed and no longer covered by glaciers. And you'll also notice North America moved a little bit northwestward. And we see Baja California, which looks like it's close to Alaska, and Alaska is now on the opposite side of the planet, close to Asia. Let's go a little bit further. Another 100 million years, so 150 million years into our future. And this is the prediction that scientists make based on the current direction and speed that the continents are moving today. We see that the continents seem to be moving and shifting backwards toward each other again. You might also notice that North America seems to be smaller. Now, why is that? Well, if we look at the continental shelf around North America. It seems to have grown. And the reason for that is a portion of North America is underwater near the coastlines. What could cause that? Well, there's no ice on Greenland anymore. Greenland ice cap must have melted, and portions of Antarctica are still exposed. So that ice has melted and added. Even further on, boys and girls, 250 million years into the future, scientists predict that we will have another supercontinent, and they're calling this supercontinent Pangea Ultima right now. And what do we get from this, boys and girls? We get from this that the continents have been moving since the beginning of time. The continent Pangea certainly was not the first supercontinent to have been part of planet Earth, nor will it ever be the last.